My name is Eli. I work at Google, where I lead the security and anti-abuse research team. Today we're going to talk about how to use machine learning to reduce side channel attack surface. Before getting started, it is worth mentioning that this talk is a joint collaboration with many collaborators around the idea of how we can harden hardware cryptography to create more secure devices. At this time of recording, which is July 14, happy Bastille Day, the results are still a little bit experimental. All you're going to see is working, but I expect by the time you will see this recording at Black Hat, the result will be way better. I hope we get a chance to discuss about recent advances between the time of the recording and the Black Hat during our Q&A session. So, side channel is one of the most efficient ways to attack secure hardware because it does not attack the algorithm, which is well vetted, but instead targets the implementation of it, which is less vetted, either because there are many of them, and also because some of them are kept secret to ensure that they are compliant with certifications. An example of how powerful side channel attack might be is, for example, this attack, which occurred a few years back, where people were able to lift out from a Trezor, which is a hardware Bitcoin wallet, the private key of Bitcoin wallets. They show you how powerful it can be and how devastating having a side channel attack can be for secure hardware. One of the problems when you develop software and when you develop hardware compared to software is that debugging it is harder because we have to find where the side channel attack came from, which means where is the leak into the code. And this leak is usually due to the interplay between the software and the hardware. And so you have to look at both of them at the same time to get an idea of what might be leaking. This is what makes it so hard. So if we were to have a more secure or the most secure hardware possible, we need to help reduce the cost of finding the attack and being able to pinpoint them accurately. This is why we ask the question, is there a way to create a debugger that will help us to pinpoint accurately and quickly what is the part of the code which is interacting in a way with the hardware which makes it vulnerable to side channel attacks? And the answer is yes, we do believe that by combining deep learning and dynamic analysis, we'll be able to quickly and efficiently find the pinpoint and quickly find the origin of the leakage, right? The leakage being where is the implementation is giving information that can be used to extract the key. And of course, because I use the word deep learning, you might be a little bit skeptical and say, well, yet another talk about deep learning, machine learning, I'm going to sell you something. The truth is, we're not. What I'm going to do today is actually show you an early prototype of a concrete software that we have developed called SCALD, which stands for Side Channel Attack Leak Detector, which is able in practice to help us find where the leakage comes from and help us debug side channel attacks. So to make it very concrete today, what we're going to do is I'm going to show you how we can use SCALD to find where a tiny IRS implementation running on an SMT32 F4 is leaking. This is obviously a unprotected implementation, tiny IRS, which is running on a well-known ARM CPU. And this combination of tiny IRS and SMT32 is what we call a target, because as I said, the side channel attack is due to the interplay between the implementation and the hardware. So how are we going to get there? First, I'm going to briefly recap what side channel attacks are. Then I'm going to tell you very briefly, how we perform side channel attack, which are using an AI deep learning, which is what we presented last year. Then we're going to talk about AI explainability, which is the core of the technique we are leveraging to do the debugger. And finally, I'm going to show you how in practice we use it to find leakage into our target. So if you want to follow along at home and you want to look at where the code and the slides as we go through the presentation, you can get them at eli.net/code. A quick disclaimer about this talk. The goal of this talk is to provide a high-level overview of how the whole thing works and provide you an end-to-end view of how the process works. If you're interested in more technical detail, like the exact machine learning architecture we use or how we do the code mapping and everything, you should have, by the time of Black Hat, a technical paper out that you can download and you can read, and we will provide you all the detail as well as code to enable reproducibility. So, with that in mind, let's start by what are side channel attacks, so everyone is on the same page. A side channel attack is basically an indirect measurement of a computational result, which is done through an auxiliary mechanism. So what do we mean by that? Well, sorry, before getting there, why is it useful? Well, a side channel attack is used, as I mentioned in the intro, to recover encryption key. It is also used in the world of web security to perform blind SQL injection, where you cannot see the result of the injection, so you have to guess what is the result. It's also used to steal password and pins, and finally, it can also be used to extract, as we showed in the example earlier, extract crypto wallet private keys. So basically, everything which is secret that you cannot observe directly, but you wish to guess or to recover, can usually be targeted by a side channel attack one way or another. So in the case we are interested in, which is hardware crypto, the idea is when you perform a computation on a CPU using an algorithm, you feed in your data, which is your plain text, and your secret key. And then as a result, you obviously get the encrypted text, but you also get a bunch of leakage. So leakage basically are these kind of side effects, unintended side effects, which are due to the algorithm running on your target. So for example, the algorithm will take some time, and unless your algorithm is protected against timing and is constant time, you will see different execution time based on the input. Similarly, and that's the one we're going to focus on during this talk, you might have leakage which are due to power consumption. So depending on what operation is done, you get different type of power consumption, and you can actually extract that. Similarly, depending on how powerful some part of the CPU might hit differently, this is not really used for recovering hardware crypto in our case, but this is something which do happen. And finally, last but not least, you have EM, electromagnetic emission, which is also very powerful, and is the other way one of the other way you can extract and recover a key. So here's an example for power trace, because that is the goal of our talk. As you can see, this is a power trace which was captured during the execution of AES. And if you look closely in the middle, you will see that you have 10 spikes. It turns out that each of those spikes is actually describing or is actually representing a AES round, right? There is 10 rounds for AES 128, and we can see very clearly on the trace that those rounds are visible. If they are visible, then they might contain information. If they contain information, we might be able to exploit it to recover the key. So that is what a side channel attack is. So to formalize that a little bit more, what happened is the CPU computes the encryption, and what we do is we measure the current with an oscilloscope, and then in the traditional setting of side channel attack, you perform something like a template attack, which is you take all the traces collected, you collect a few of them, actually you don't collect one, and then you combine them statically to try to pinpoint what is the key value, and then you recover the key. That is, in a nutshell, what a side channel attack is. In our research, because we got the question asked a lot, what do we use? We use NeuAE ChipWhisperer Pro, and we sometimes use a Picoscope 6000 when we need faster sampling rate, depending on the target. In this talk, that being said, we only used the ChipWhisperer Pro to do the capture of the trace, because we are going to use synchronous traces for only the first few rounds. When we do, as previous work, the whole traces for the whole implementation, and we want to do it in the attacker settings where we don't have the clock. We use also the Picoscope. Again, this is not an endorsement for a product or another. It is just that this is what we use in our lab. So if you would like to reproduce our result from the ground up, this is what you could use. So let me now describe a little bit more of how we wave in deep learning, because we're going to need the machine learning model generated during the attack for the debugging. So deep learning Sidechain attack, we call them sidechain attack automated with machine learning. And the idea is you're going to replace the template attack with something else, with a neural network. And this is something we have covered in detail before. However, I'm going to briefly recap today how you can do those attacks in practice so you are able to figure out, to get a gist of what is happening. If you would like to have a more in-depth explanation of how the whole thing works, we had a talk last year at DEF CON where we actually get into greater detail for 40 minutes on exactly how that works and all the nitty-gritty and bits. And you also have the code associated with it. So if you want to go there, you can just get the slide and the recording of last year's video at that address. All right. One thing which is different from last year and which is different from our threat model where we try to do a black box attack, which is the strongest thing we can do when we try to evaluate the security of a chip. In that specific case, we are building a debugger. So we are building a tool which is for the people who built the hardware or are not necessarily building the hardware but are creating the secure token. So we are taking a white box attack model, which is we have access to the source code, we have access to the clock, and we have access to knowledge about the implementation. As a result, we are simplifying the attack by using synchronous capture, which means we are using the internal clock of the target to capture the trace. It makes it easier because we have traces which are perfectly aligned, which you don't have in the black box settings. We also are reducing the amount of point in the trace that we are capturing because, well, we know that we only need the first round and a half or something like that. So that makes it easier for us to train the model because, of course, the trace is smaller and well aligned. So the model has to do less work, so we can use smaller models and also it converges faster. It's easier. You could do it with the full SCAML model if you wish, although it's going to create a lot of dead space. Which is not necessarily useful for this type of stuff, as we want to have as quick of an interaction as we can. This is why it's a white box model. This is why we did choose a white box model. Okay, so how the SCAML process differs from the SC8 processes that we saw earlier? Well, we start with the template, which is you perform the second. My Google Assistant decided to carry over. Sorry about that. Unexpected during, but given the condition, the phone is not just here. All right, so let's go back to where we were. So we have the encryption, and then the encryptions, basically what happens is the encryption is performed as usual, and then we capture the signal with a chip whisperer, right? And then we get a bunch of traces. And then instead of doing the template attack, what we do is we feed those to a deep neural network, which is deep learning, a form of AI. And then the machine learning is going to emit a prediction, and we're going to combine them to recover the key. And that's what it does. The advantage of this technique is it's fairly automated, doesn't require too much domain expertise, and also can work on very complicated target quite efficiently. As I said, it works really well in black box settings on the full traces, which is something that other type of approach struggle with. When you do targeting, by the way, when you do target an implementation, you might try to target directly recovering the key. But more often than not, we try to target what we call intermediate, which are part of the AES where there is some sort of memory loading or memory unloading, because this is where the power is changing, right? Because you are setting some bytes to 1, some bytes you are inputting to 0, so the power is changing, right? So we want to have this kind of point. Those points are called intermediate point. There are quite a few of them. The three canonical ones that most people use, including us, are the first initial three, which are part of the initial round of AES because they are easily invertible, which means you can directly recover the key from them. Today, we're going to only focus on one of them, which is subbyte in, which is basically the intermediate point which happened, as you can see on the diagram, after we have XORed the key with a plain text. You could target also subbyte out if you wish. As we explained earlier in the previous talk, trying to target the key doesn't work really well. This is not a vulnerable point for TinyARS, so your model will probably not get as good of an accuracy. And given that we are trying to get for the most obvious leakage for now, sub-byting is perfectly fine. Okay, last thing I want to mention before we move on to how to do the debugging is what do you do with a prediction, because that's one of the nice things about machine learning when you do deep learning based SCA, is that you get your traces and then the model, instead of telling you one value, it will give you a probability, a fake probability, but a probability to a softmax will tell you for each value of the intermediate what is the probability or how strongly he believes each of them is a correct prediction. So what you can do that gives rise to a very natural probabilistic attack where basically you take all the output of the model. So the model will tell you for each value, potential value, what is the probability, so you can actually sum them using a log 10 plus epsilon, and then you get a distribution. And that helps you to accumulate probability very easily and tell you which is the first guess, which is the second guess, third guess, and you can actually rank your guess. And so it's a very nice probabilistic attack that only deep learning provides. So that's also one of the benefits of using deep learning based SCI, SCAMO. All right. In this current, to make things, to give you a little bit more detail, the model we're going to use in this talk is something called a simple hypertuned residual separated 1D convolution networks. Basically what it means is we use 1D convolution. We use separated one because they are faster and have less parameters, and in our experience over the last 3 years, it feels that it's good enough. It actually gives us performances. It is able to work and converge, so we don't need the full convolutions. We also have hypertuned them before, so we basically use one of our best models. And then it's a convolution network, which means it's mostly based on convolution. And the residual part means that we tend to do something like the ResNet implementation, which is basically we do a bunch of convolution and then we keep the signal by having a second path that you can see on the right side of the diagram, which helps us to keep this to maintain the flow of the gradient and avoid vanishing gradient problems. So again, it's fairly standard if you do machine learning. It's just adapted to work well for 1D traces, and you can construct your block differently. It seems that this block is the one which works best for us, and basically we stack a lot of them like pancakes, which is why it's called deep learning. Here is an example of what you might get if you train this model. We have 3 models which are trained because we trained 3 models for this talk. In a real setting, you will train 16 of those, obviously. And what happened is basically you can see those 3 bytes converging very well after only 10 epochs. We could have kept going to increase the accuracy, but at that point, each model have reached above 60%, which is plenty for what we try to do, which is get a bunch of traces where the model is able to predict the correct value and then use that to debug. So that's plenty enough. So we stop there because obviously we want to have to be as efficient as possible. As you can see, the important part here is you can see that the validation, so there is two curves for each of the point, is actually tracking very closely the training set. And the reason that's really good, which means the model has generalized perfectly because both are tracking each other. So we have a model which generalizes well, so that's a good model. Again, that is expected because we made it very easy for ourselves by having an unprotected implementation, TinyARS, and make it synchronous and shrinking down those traces to only the first 4,000 points. So that's what it is. Last but not least, as I mentioned on the side, if you're not familiar with how sidechain attack works, we do tend to recover 1 byte at a time. So you need to recover the whole key, 16 models, and then combine the prediction to recover the whole key. For the rest of the talk, I'm going to only focus on 1 byte at a time because you basically repeat the same thing 16 times. I'll show you some example of how the debugging looks like different from both traces for different bytes. So keep in mind that we have multiple models. Okay, so now we have a model and we know our model is efficiently breaking TinyARS. So the implementation is broken very, very badly. So, okay, can we use that now to figure out where the leakage is coming from? Well, yes. To do that, we're going to leverage a known technique, known set of technique actually, which is deep learning explainability. Deep learning explainability actually was developed for vision at the early stages. So they had a bunch of data sets, and the model, for example, will accurately predict in this image that it contains a boxer and a tiger cat. The question is, why? What is the part of the image that the machine learning is using to decide whether there is a boxer or there is a tiger cat? You want to use that to make sure there is no biases or errors into your data set that are giving hint to the machine learning that it should not pick up and it did generalize correctly, right? You want the machine learning to not only detect a cat in that image, but also detect it in any wide range of images. So you want to make sure it focuses its attention to the right place of the image. So the way you do this is, as I said, to answer that question, the way you do this is you use an explainer technique. There are a few of them. I'm going to highlight a few of them after that. And so basically what you do is you feed to the explainer the model, you also feed the image, and then you ask it why this class was predicted. You can ask the main classes, or you can ask a class which is not the main one. You can decide which one you want. But basically what you're doing is you are conditioning the explanation based on the prediction you want to explain, right? So you basically provide the input and the output. In a way, you can think of an explainer as something which reverses the model, right? It's not really what it does, but what happens is you basically, the output of your choice becomes the input, and the output becomes the image itself. And if you do that correctly, you get something nice like this, which is, well, if you are trying to predict the boxer from this image using that model, and that's a true example from a ResNet model, then you get this nice heat map, which we call leakage map later on for traces, that basically highlight that, well, it mostly focuses its attention on the face of the boxer. So we have some confidence, at least, that the model is looking at the right part of the images to make its decision. We can confirm that by doing the same thing for the cat, right? Which we say, hey, explainer, take the same image, take the same model, but now tell me why you came up with the idea of a cat. And this time it's looking at the body of the cat. And because it says a tiger cat, it's looking at the stripe. So far, so good. That seems okay. So we are fairly confident that the model is actually working as intended, right? Here's an example where actually this type of technique were used to find biases. Very, very early on, there was this very famous data set for images called the Pascal vocabulary, right? VOC data set. And early on, this data set has this interesting feature that for horses, I think 1 in 5 had a text box on the lower left. And what happened was that the machine learning was predicting there is a horse, not because there was a horse in the image, but just because there was a box. And so that was very interesting. It was a biases which were due to the fact that the image had a statistical discriminator, which was easier to learn, there is a box or not, rather than learning the shape of the horse. This was basically the initial major success, I believe, for this type of explanation. It was done into a paper called Unmasking Clever Hand Predictors and Assessing What Machine Learning Really Learns, which was published in Nature. I believe the paper is widely available, not even without a paywall, so you can check it out if you're interested into the origin of explainability. So that tells you how we do explainability, but of course now the question becomes, okay, how do we use that and how we combine it with dynamic analysis to do what we wanted to do, which is find where the leakage comes from. Well, this is where Scald come into play, right? This is our debugging tool, which is written in Python. And so the game plan we have for Scald is, well, start with an explainer, of course, and we're going to do very similarly. We're going to feed it a model, which is our trained model we see earlier, and the traces and the prediction for the traces. So we only keep the traces and prediction which were correct, because we're interested in why the model correctly predicted given the output of the byte in. And then that's going to give us a leakage map. Of course, it's 1D, this time because it's a trace, it's not for 2D like the images, so that's what the leakage map is. And so basically our hope is that the silent point into the leakage map will correlate with the code of that. But if you have a leakage map, you just know temporarily where it is. It doesn't tell you which instruction it is. So we need a second piece of code, which is where the dynamic execution come in, which is the target emulator. So if you remember, the target is the code running on a given hardware. So for it is TinyRS running on an SMT30F4, And so what happened is it's going to take the leakage map and then it's going to execute the target, and basically based on that, and we're going to get the execution timing, and we'll be able to correlate to know what execution was executed in which part of the traces. We're going to glue everything together and use debug symbol, and you should be able to get annotated code with the leakage map and say this is the code line which is the most likely to leak. Okay, so how we get there? The first thing we had to choose is what type of explanatory technique we should use. So we started by that, right? We need some explanation. So there's a ton of them. Here is some of them which were developed, and you can see you get more or less a defined images or a defined output. The one we do use out of those is the one in the middle, which is a guided gradient GradCam, which is actually we use GradCam++, which is a improved version because it's one of the most well defined. We do also use something which is not displayed here that I will cover later on, which is the activation map, which is literally just looking at the output of the first layer. So now that we know there are a ton of techniques, the question is, how do we choose the best one for our job, right? And the answer is we have to benchmark them. So the way we benchmark them is we take every explanation we get for all the traces we get. So we use, 4, 5, 6,000 traces. And for each of them, we apply, we explain them. So we create a collection of them, as you can see on the top left of the slide. And then we combine them by either averaging them or summing them, it depends. And then we filter them to only keep the spike. This is the orange part of the second boxes on the left. And then we normalize between 0 and 1 because we want a fake probability of what is the most important spike, right? And then when you have done that and we have eliminated everything which is below the average plus one standard deviation, you get what we call the leakage map. And you can see the leakage map generated here seems to have one initial spike at the beginning and then one larger spike at the end of the traces. Again, the end of the traces is probably the end of the first round. Actually, we think that for this demo, I cut it a little bit too early. I should probably have taken 6,000 or 8,000 points, so we might miss the end of it. But suffice to say that for this byte, it seems that we have one input and one output, right? So the thing we can do is we can generate those heat maps for various techniques. So the first technique we use is the SNR, right? The signal to noise ratio. This is not the deep learning technique. This is the very old technique which was developed actually to do traditional side channel attack, which is actually built in with ChipWhisperer, and we use that as a control. We want to make sure that we might also use it, by the way. But the idea is this is signal to noise ratio. This is a standard technique where you look at given some assumption, where is the spike, where are some spikes based on this notion of where is the most discriminative part of the trace. And as you can see, this seems to be, this is for byte 0, something at the beginning and something in the middle, and then nothing. Then we have the GradCam++. As I said, the gradient cam is this idea that we use the integrated gradient and we compute some sort of an inverted model where we use a gradient to see how it flows from the input, the output, back to some of the layers, in our case, the initial layer, because we want to look at each point individually. And you get a very, very different map, right? So we already know that one of them will be more correct than the other one. And then a third technique we use is called the activation map. So the activation map is basically you do your prediction and then you look at what were the value of each of the different, how much each neuron did fire, right? And so because we use the lowest bottom layers, and these layers is the size of the trace. We can get for each of them how much it did fire. And what you can see here is it's mostly identical when filtered to the GradCam++. So both of them are somewhat identical, so we expect them to be performing roughly the same. So how do we evaluate the quality of this? Well, the idea is very simple. We have our test traces, and we have our leak map. So what we can do is we can decide to suppress, which is basically putting the point to -1. The machine learning normalized between -1 and 1 in our case. And then we remove them. So what we can do is we can take what are the 4, 6, 7, 8, 20 points. After that it becomes meaningless. But the first top point that are reported by the leak map, suppress them from the traces, feed them again to the machine learning model, and look at how much the accuracy did decrease, right? So basically what will tell us is if those points are important for the machine learning to the prediction, the accuracy must go down. If the points are in a dead zone, the machine learning might not care as much. It do care about everything, so you'll see always a decrease, but it might not be as drastic. So now the question becomes, if we fix the number of points, how much of a sharp decrease we do? The one who decrease the most the accuracy would be the technique which is the most predictive of the leakage, right? That's the technique we're using, and that's how we do benchmark our explainability technique. So baseline, as I mentioned, is 100% because, well, we only kept, as I said, correct predictions, and then we can look at each of them. So the first thing we can look at is, as I said, signal to noise ratio, and in that case, on byte 0, the drop of accuracy for 4 points is dropped to 57%, which means we have a 43% reduction. So almost half. So in 4 points, there are 4 points. The SNR top 4 points are responsible for about 50% of the accuracy of the model. So it gives you an idea that these are really where the leak are coming from. Similarly, fairly consistent with byte 7, where it's even deeper, 44%. Now, if we look at activation map, that's where we start to be really sad. At least we were very sad. The activation map performed really worse than that. So about the same for byte 0, but then for byte 7, what the leakage, the activation map return is not predictive at all of where the leakage comes from, or at least not given our benchmark. So we're hoping that GradCam++, which came as one of the, not the latest, but one of the most well-used one and is supposed to be really good, at least work really well for images, will work well for us. The thing is, if you remember, I showed you they are almost the same leakage map, so you get the same result. I mean, that's consistent, that's good, but the numbers are really, really bad. We still, again, don't get as much as the SNR, which I told you is a simple statistical test, which use hypotheses which we know are not as accurate as the machine learning one, because they use the Hamming model, if you want to be precise. So we were really sad, because, and it took us a while to figure out what to do, because actually the explained technique we wanted to do not work, and the SNR, and also, as you have seen, we could have said, well, but they are cleaner. They're not. They also have a ton of stride, so they're not very informative either. So it took us quite a bit of iteration back and forth, and then we ended up deciding that we need to create something which is a little bit more tailored to what we wanted to do. So the reason why that might work, and I know you might be skeptical that we can come up with yet another technique and why it will be better. So the reason why it might be working better is because usually the machine learning technique used for explainability focuses on the highest level features, so the upper part of the neural network, to get more of this understanding. And what they do is they stretch, because the neural network is like a pyramid, right? So the upper layer are smaller in width, so you have to, if you want to put it back to the trace, you have to stretch them out. We don't want to do that because it basically creates inaccuracy, so we try to do the explanation at the lowest layer. It doesn't work, right, as we saw. So we were hoping to go back to the roots of the idea and actually use one of the oldest techniques, but revisit them to make it a little bit more precise, which is using occlusion. So the problem with occlusion is that an occlusion is basically you are removing part of the trace and you're scanning it that way. The problem with that is, of course, it doesn't take into account nonlinearity. So to combat that, we came up with a novel version, which is basically combining this type of occlusion by block with a convolutive occlusion, which is basically using a windows and then convolving the squares to get some sort of a back of the nonlinearity over a large region or a small region, like a set of small region. And so what you end up with are the maps that you can see here. So the first thing about those maps, just visually, is they look very clean, right? They are only very, very few spikes, so that's good. If they work, it's very clear where the leakage comes from. The other thing which is very encouraging is the byte 0 leak map clearly show leakage before the byte 7. Of course, the algorithm process one after each other. It's not using any kind of SIMD or vectorized operation, so that's what we expect. We expect it to do one, then the next, and the next, and the next. So we're pretty good, confident that actually makes sense. It also interestingly shows you that product byte 7 actually is really close to the end of the traces, which explains why, as I told you earlier, I might have cut the trace a little bit too short for byte 15 or even byte 13 and so forth, because we're already at a limit for byte 7. That's why we did cut here. And so yeah, it looks good. So now we can benchmark it. And the answer is how good it is. The answer is pretty good. It's way better for byte 0, 17%. So way, way significantly better than anything else. And for byte 7, it is better than SNR. Not by much, but it is better. To be honest and to predict that, that's for 4 points. When you look at 5, 6, 7, 8 points, sometimes one goes above the other, but overall, Skold perform better. So we have a technique now which works really good, really well. And if you compare the quality of the traces, the first thing you will notice is actually the Skold traces is very similar to the SNR one for byte 0, except it's way more defined. Most of the noise that were plaguing the SNR is gone, so now we have two very clean part of the traces that we know is responsible for most of the leakage, which is good. Also, Skold believes it might not be very visible on the slide, but there is a red bar in the middle. So Skold believes the second spike is more important than the first one, whereas for the SNR, that's the reverse. So interesting, the differences between the two. And in the middle, I put GradCam++, and you can see this trace is non-informative. So we have confidence. We are finding almost the same places, so we are confident it actually makes sense. At least it actually makes sense from even a statistical analysis. So that gives us a lot of confidence that it's the right technique for the job. So now we're back on track. We have a technique which decreases accuracy the most and have very, very low noise. So when we use it to explain the code, the developer only have a few places to look at, which is really good. So now how do we go from the leakage map to the code? And this is where I'm going to be a little bit hand wavy, because this is a part of the code we are still actively working on. And I don't have a slide to show you the end result, but I will explain you where we are at, and I can show you where we are. So the idea is how we go. The first thing we need to go is, as I said, you go from the traces to CPU instruction. So CPU instruction is going to depend on two things. The first thing is what type of CPU you're using. So we're using an ARM. So we need to know for each instruction how many cycles it takes. Then we need the firmware, which is basically the compiled version of the code, which tells us which instructions are executed. We need to feed the leak map, which tells us which points are important for us. And we also need to have a state automaton who instrument the emulator to be able to reproduce the encryption. And so we can basically reconstruct what instruction were executed at which time, and then map it back to the trace, which will tell you what point in time is important, right? So with all those things, what you get is you get a heat map of which CPU instructions are the most important. This is the part we are still actively developing, because we need to refine a little bit how our clock and program counter are implemented to be as accurate as possible. But this is what it does. Then what we need is, now we have assembly code, so we can probably end up there, worst case, but we want to go one step further, which is, can we go back from assembly code to C? And this is something which is well known in the security community. That's what is the bread and butter of reverse engineering. So there's a lot of product to do that, but essentially what you do is you take your ASM, and then our firmware was compiled with debug code. Again, we're in the debugger setting, white box. So we know what debug code, and then the debugger can easily go back from instruction to line of code thanks to those debug symbol. So from there, it's fairly trivial to go back to the leak code. So now we have the code alongside the heat map, and hopefully, well, then now you know which line of code is causing the most leakage according to machine learning. And because, as I showed you earlier, the machine learning explanation is very well correlated with the SNR, we believe it's also going to surprise the template attack, which uses kind of statistical ratio. So everything should fit together. I wish I would show you for 10 years the exact line, but as I said, at this time of recording, July 14, we are not there yet. We are still refining it, so hopefully we'll get that by Black Hat. All right, so the idea of Scald is that we can build this tool which is going to hopefully empower developers to quickly figure out what to patch and focus on developing stronger crypto more than how to do this side channel attack and everything, and freeing up more time to focus on design and experimenting with new masking technique or protection or things like this. We are really excited to test it more and have a little bit more use cases for it and show how bright, how well it generalizes. So far, we are very hopeful it's going to do that and it's going to help us. The main benefit and takeaway from this talk should be that as we mentioned also last year, machine learning is a way to perform state-of-the-art SCA attack automatically. It actually is changing how we approach a side channel attack because it's allowed to automate a lot of things and also take into account linearity that we were not able to do before. However, they also have, as I showed you with the leak, how the leak map actually aligns, that they're also finding the same type of stuff that you would find with SNR, plus more. So it's literally a upgrade. The second thing is we showed you, and that's the meat of the talk, how we can actually combine this AI capability with dynamic execution to try to find leakage almost automatically, and then helping reduce the development cost of secure hardware, and hopefully would help us to have more secure hardware through the world. And finally, there is a lot to be done. While this talk show you a way to do it, we don't claim this is the best way, just a first step towards that idea. There was other research, by the way, I need to mention, who are exploring the same idea. Some of them from the ANSI did some of this type of research as well on how to use explainability. I don't think they went as far as us, but this idea is explained in the community, and it's a very active community. So there's a lot of work to be done in the idea of applying AI for side channel, whether it's for improving attacks or improving defenses. And so we're really excited to see how this is going to turn out and have collaboration with as many people as we can, so we can build the most secure hardware we can. Thank you so much for attending this talk virtually. I hope you're all safe at home. And then if you'd like to keep up with our research and figure out how we make progress and be aware of new release, you can always check out the website. And you can also follow us on Twitter, where we try to post our update. Thank you so much for attending. Oh, I'm sorry. Yes, it was. I apologize. I was saying thank you so much for you guys for attending the video. I hope you can hear me now. And can you guys hear? Yes, no? You should be able to hear me. Yeah, yeah. Thank you. So, okay, sorry, there was a problem with the audio. So I said thank you so much for attending. As you have seen, the talk was 3 weeks ago. So about 3 weeks ago, so we didn't get all the results in. I did add them to the slide deck, and if you take the latest slide deck, you'll see that we actually did in the end using our tools code. The question was, which tool we use? Well, that's our own tool, and we're going to make it available on GitHub, and you will be able to play with it and reproduce the result you saw. And then you will be able to retest what we found. And actually, in the end, we are able to find and to see that yes, Scald, which is our own tool, actually find the leakage exactly, which is to the exact line of TinyAS, which is the one which do sub-byte in. So we have confidence that it works at least in that case. Now that I was saying and answering the question, it is very, very difficult to get it to work because you have to emulate perfectly the cycles of the CPU. So we have to be cycle precise, and the connection have to be to the exact point. So the research paper that I was mentioning is going to appear a little bit later. We are trying on different implementation because we don't know what we can do or can't do. So I hope that answered your question. Thank you so much for attending. I'll take more questions during the Q&A, I guess, in the green room, and then really appreciate you bear with me and with the Google incident, and hope you find it interesting and inspiring. And as usual, always happy to answer questions on Twitter or by email. Thank you so much for attending.